Thanks a lot. Good evening, everyone. Moin Moin, Hamburg. It's a pleasure to be here. This is not for making advertisement for the delicious Moritz Fiege beer from Bochum, but it's rather for medical reasons to soften my voice. So the talk, we can't see anything, can we? Can we put slides on? Beautiful. So, title of my talk is Milking the Digital Cash Cow. This relates to a fairy tale of the Grimm brothers. The German, there's a gold esel, and if you say something mean to the gold esel, he shits gold. And I noticed here on the 29C3, if you say to certain girls, you say something mean, you get a red card instead. No gold here. So we are going to milk the digital cash cow. And I'm coming from Bochum, from the very west of Germany, from the Ruhrpott, where the air is very black because of the coal mines. But if you take the picture from the right direction, the Ruhr University is very beautiful. And right there is the Horst Goerz Institute for IT Security. That's where I am a researcher in this HGI Institute. I'm one out of 100 researchers there. And we also have a lot of students, 600 students in IT security. So you can study IT security in Bochum. I can recommend this. You can first do a six semester bachelor studies, and then after this a master either in information technology, or if you went to Fachhochschule or you studied something else before this, you can make this master in networks and systems, or if you're working, you can do distance learning. And that's what I am doing. So I'm now very proud to be in my 27th semester studying electrical engineering and information technology, and did a lot of research. And in this, I'm going to show some of this here. But first of all, so 30 years ago, this is my first computer. 30 years ago, 1982. I remember it exactly. I was about 3 years old then. This device was first introduced, the Commodore C64. May I ask, who in this room has or has had such a computer? Okay, it's at least more than half, more than half of the room. And it's a very beautiful computer, and because it's to celebrate the 30th anniversary of this computer, I have decided that in parallel of my talk, we will play a nice Commodore C64 game. And my favorite Commodore C64 game, which is the game Mafia. Is it known to everyone? It fits quite well to the talk. So we first have to load the game. Mafia. Yeah, it's not so. We used to have a lot more time for drinking beer while booting the game in the old days. But we have a floppy accelerator. It's starting. So the game is, this is the beautiful graphics of the Commodore C64. 32 kilobytes of memory. And of course, first, before we start, we should cheat a little bit. So in line 350, this is the random number generator. And here we give us some more, let's say 30. To be, otherwise the game will take ages. So we can start again. Compare the 32 kilobytes of memory to the size of one Microsoft Word file. So the game starts. How many players? One. It's me, Timo, GMEH. And now it's about, I get some force, I get some intelligence, brutality, and some start capital. And the game can start. Nice sound we have. And now we can walk through the city. Usually the first thing you do is you go and organize a car. Organizing a car. So you go to the car shop. You go inside the car shop. There's another nice graphic. And what you can do in the car shop is you can buy a car or you can organize a car. Of course we want to organize a car. If it's not okay, but there are too many people here. We can try again. Organize the car. Still too many people, so we go to the next round. Let's assume we have the car now, because we don't have so much time. We have to start with the talk soon. So let's at least go to Blüteneddy. Blüteneddy is very important because you can go there. This is Blüten Eddie. He's printing counterfeit money. Yeah, Blüten Eddie, my favorite. But he's, you can ask him to forge a passport. Number 1. This is another talk. We are not going to talk about this. Do you still print forged money? Yes, that's what you want. 2. So how much do we want to invest? 5,000. And he gives us some counterfeit money. And the cool thing is you can go again and again to Blüten Eddie and again give him his own counterfeit money, and he will again return you more and more of this money. Huh? And this is how you have to start with the game. Okay, but we should not forget the talk, so let's not play Mafia all the time. Huh? So we have seen Mafia, it fits very well. And this is maybe Mafia 2012. Yeah? So this is the content of the talk. I start with some introduction about wireless devices and such, and then I introduce the topic of side channel analysis at hand, a very, very old story, keylock door opener. Some of you might have seen this already on the 25C3 when we presented the whole keylock story here with Thomas. And then come the MyFair Desfire MS3 ICD40. I'm already fluent with the MS3 ICD40. Contactless smart cards, how to extract the secret keys of these secure smart cards. And then finally comes the third part, a contactless payment system, probably the worst realization of a contactless payment system ever. Now, this is a joint work with Ingo von Maurich, David Oswald, and Christoph Paar, with my dear colleagues. All right, and this is what my research in the past years was about. So all these embedded wireless devices, you all will have some like this in your pockets, like to open doors, for contactless payments, identification purposes, for ticketing, to open and close your car, for governmental identification, or here these RFID enhanced pacemakers that you can reprogram through the human tissue. Here the attacker model is accelerated heritage, like set the heartbeat of your grandfather to 220 beats per minute. This is not part of the talk. So what all these devices need is cryptography. And cryptology they need, the core of all of these. And if you look into cryptology, you have on the one side always the inventor of a cipher who invents some cipher, cryptographer. And on the other side, you have the attacker, the cryptanalyst. And the game is that the designer invents something and it's tested here, and if the attackers find some vulnerabilities, they will report it to the designer and he can improve his system. And this is the very important circle, how to design a secure system. It's well known in the mathematical world. It's not yet so well known with attend of real world devices. And there's a recent trend that people do such cryptanalysis attend of real world commercial devices. And surprise, today on the Chaos Communication Congress, we are on the side of the attackers and we do some security analysis here. Looking deeper into the field of cryptanalysis, we have to do this here to distinguish what we're doing. We have got the classical cryptanalysis. Classical cryptanalysis works at hand of a mathematical model and abstract description of the cipher or the cryptographic thing you want to analyze. So you can do brute force attacks, given a plain text and a ciphertext, try all possible secret keys until you find the correct one. Then you can do protocol attacks, for example, man-in-the-middle attacks. That's the modern way of stealing cars. You have seen these recently in the news, the passive keyless entry systems, how to drive away the car with man-in-the-middle attacks. And then we have the classical mathematical analysis. This is what Nicolas Courtois is doing in the other room currently with the Russian cipher Ghost. So really hard mathematics. And we are now on the right side of the picture, where this, say, very secure cryptographic primitive is put into an electronic device. And there we have completely new attack vectors. Say you have got it in your smart card, on your mobile. Then you can do some implementation attacks. For example, active implementation text is fault injection. For example, you manipulate the power consumption, the power voltage supply of the device, or you shoot on the circuit with lasers, optical fault injection. You want to induce a fault and then somehow extract the secret key. Or you do reverse engineering, either from software, so you disassemble some code and you look for the secrets in that code, or as Carsten Mohl did years ago with the MyFair Classic chip, you reverse engineer from hardware by taking microscopic pictures. And we are now focusing on the side channel analysis, which is a passive type of attack, which means that the device is operating under its normal operating conditions, and we just passively observe it while it's doing its normal things, and then we try to conclude with the secret key. And I would like to explain this at hand of a bank robbery. Yeah? So say you have got this safe here, and you want to open this safe. What you can do is first you can try all possible combinations of this lock, do a brute force attack, and you will try for years and years, and you will never open this Tresor. But there are different approaches. So let's see how it is done in Mafia. Yeah. Back to Mafia. I saved some state because to break into a bank in Mafia, you first have to have a certain criminal status. You first have to be at least kleiner Fisch. And here I'm already Ganove, so this is a freezed state. Ganove. So let's go to a bank. We're going to the bank. It takes some time. The bank is on the left side somewhere beside the supermarket, this white thing there. We're going to the bank. Enjoy the nice graphics while I enjoy a little bit of Figeview. Okay, we walk inside the bank, and it says, good morning, sir. What do you like? You have two options again. The first option is, this is a bank robbery, and you directly take the pistol and rob the bank. And the second option is, just look for alarm systems and come back again in the night to rob the bank. That's what we want to do. Who wants to do the break? That's Timo with his revolver. Now comes the important thing here. It says, let's see, I want to try it with a stethoscope. Yeah, so we will use a side channel of the Tresor, the side channel of the mechanical lock while turning it in order to find the correct positions of the combination locks. So now silence here in the room, because we are going to, with the F keys, going to break the Tresor. Oh, this was bad. Probably there will be an alarm. Ooh. This was my fault. Okay, an alarm here. Not successful bank robbery. Oh, that's bad. That's bad. Something went wrong. Devil. Oh, that's bad. But I hope the principle, I think there is no time now for this shooting thing. It will just take too long. I hope the principle of the side channel attack has become clear. So the professional thief just takes this stethoscope and listens to the sound of the mechanical locks in order to find the correct combination one after another. Yeah? It's like the divide and conquer principle that we're using here. And we do exactly the same, just at hand of some electronic device which is performing cryptography. Yeah? For example, here these key lock remote controls. They're used to open cars or garages. And if you look inside such a remote control, it possesses a counter, and each time you press on the remote control, the counter is increased by 1. And then it's encrypted with a cipher, in this case the key lock cipher, and the output is then sent to the car, the rolling code. It's the encrypted counter. And now the car on the other side, it can decrypt this rolling code and check the counter value and can decide whether it's a valid code or not. I'm not going into the details here. There's a secret key used for the encryption, of course, and that's what we want to have. And then, of course, we know the algorithm and we know the ciphertext. We do not know the plaintext. And of course, here a stethoscope is not so useful because we cannot listen to anything, but we will use a digital oscilloscope instead to measure the power consumption and see. We just assume that the device consumes different power when processing a 1 than when processing a 0. And we measure the power traces, process them on the computer, and finally, if we are lucky, we get out the secret cryptographic key and can then clone the remote controls, for example. That's the idea. And this is to give you an impression what it looks like. This is one power trace. When you record it, when you press on the remote control, on the right axis the time, on the y-axis is the power consumption. The beginning is very easy, so you press on the button and the device starts to operate. The end is also very easy. This is where the rolling code is sent. And now the problem is, where is the key lock encryption here? It must be somewhere in between this. Does someone want to have a guess here in the room? Maybe you want to point somewhere? Where would you guess that the key lock encryption is? Oh, no guesses? Yeah, we guessed it would be there on the top, but of course it was wrong. This was the moment when the device writes to the internal EEPROM to store the new counter value. And after some more months, this is the worst part of all of it, we found that the key lock is just here. Yeah? So between 21 microseconds and 24 milliseconds and 24 milliseconds is where the key lock takes place. And this is what took the most time for the attack. We simulated the successful power analysis attack long time before. This was no problem. But to do it in practice, this was really hard to find where the key lock encryption is. So after performing these attacks, what is the management summary? You press 10 times on such a remote control and measure its power consumption, and then you can extract the 64-bit secret key of keylock and clone the remote control, which is not very impressive. Then we had another attack, an improved attack. There's a so-called manufacturer key in the keylock system. And we can obtain this manufacturer key from only one power measurement without knowing neither the plain text nor the ciphertext. That's quite impressive for mathematicians. They can't figure this out still. And this manufacturer key is very important for the keylock because the keys of each remote control of one manufacturer are derived from this manufacturer key and a serial number of the remote control. So each time I press on the remote control, it sends its serial number and then the rolling code. So if I know the serial number and I know the manufacturer key, then I can clone such remote control from a distance, as was shown here on German television, Dreisat, years and years ago. It's dinosaurs. But it's still, to understand that this is a more devastating attack because it leaves no traces. So we come with our car, Professor Pa and me in the car. We park in front of the garage, and there comes the victim. And the victim now opens the garage, and we eavesdrop this encrypted rolling code. And the victim is leaving. Of course, she doesn't notice us because we are hidden in the car. And now, with the help of the manufacturer key, we get the secret key of the remote control and produce the next valid counter value in order to open the garage, and then we can walk inside the garage and, for example, put something into the garage, whatever you want to do there. Yeah, this was years and years ago, and after the attack, there were basically 3 reactions from the industry. So one reaction was that companies ignored us. That was quite often. Then more often were companies that hated us. For example, I got known to the Dachverband of Garagentorhersteller the next day after the press release. Yeah, and there were also some companies who helped us, who asked us how to improve their products. They said, "Oh, we have got this keylog and we want to have a secure system," so we helped them, and they probably have not a very secure system because we helped them with it. This is interesting, but the question is, what does it mean for Mafia? For Mafia 2012, if you go to the car machine, there are now more options. So first, in 2, you can crack the manufacturer key of one manufacturer, and in 3, you can eavesdrop the code and then open the car. But of course, number 4 is the traditional way of organizing a car has to be in the list still, because compared to the efforts of extracting manufacturer keys and opening a car, the traditional way of just smashing a window, if there is no alarm system present, it's still an option for sure. So this was the very old story keylog, and it was didactically a problem because many people thought that these side channel attacks can only be applied to or mathematically broken ciphers such as keylog. So we looked for other targets, and we found the NXP MyFair Deathfire card, which is a contactless smart card, so it does not have any contacts, and it uses the triple death cipher with a 112-bit key. It's widely used for payment, for ticketing, access control, for identification by many companies and other guys. And it has a 4 kilobyte non-volatile memory. And inside this, you can create something like, it's similar to a Linux file system. They're called applications, but each application is rather a folder. And each folder can contain up to 16 files. And then you can give access rights on the file level. So for each file, you can say 1 out of 14 keys for each application what you may do with the file. Read it, write it, delete it, anything. And there's also a master key for each Deathfire card, which is like if you know the master key, you can, for example, format the cards. And it's widely used, for example, in San Francisco in the Clipper cards, or Open cards in Prague, or the new Oyster cards. I think they are also using this. This is what Nicolas Cotta just told me, but I'm not sure about it. When we started with the attack, we just had this black box. Yeah, we did not have. You don't get much information about such a product. If you wanted to have such information, you would probably have to sign an NDA for 20, 30 years, and this was not part of the plan. So we just knew that if we send something to the card, it is encrypting this value X with a triple dash cipher. We don't even get the output. Yeah, the output is somewhere inside the car, but we found out it's always encrypting something. The problem here is now that it's a contactless smart card, as I said, so we cannot measure the power consumption directly, but we have to measure the electromagnetic emanation with such a near-field probe. And it's an RFID card. That's another problem. So we first need something to communicate with the card, control PC, and to communicate with the DESFire card, we use our self-built RFID reader, and you can build it if you like. It's an open source project. There's currently the layout and the schematics. You can build it for less than 40 euros, and it's freely programmable, so you can use it also without the PC, and you can use it for practical tests in the field. This is used for the communication, and then we have on the other side we have got the data acquisition. So we've got a near-field probe here, some special digital oscilloscope, a USB oscilloscope. It digitizes the electromagnetic field and then feeds it into the control PC. Yes, and the reader also sends some trigger signal to start the measurements of the oscilloscope. And now you see already we need a very strong RFID field here to power the DESFire card. And we want to measure the very small side channel leakage of the silicon chip which is inside the DESFire card. And you can imagine that this side channel leakage is orders of magnitude smaller than this strong field of the RFID reader. So we somehow have to get rid of this strong RFID reader field first in order to conduct the attack. This is a power trace that you measure without any special circuitry. What you see is nothing. No? And if you zoom into the power trace, you see some sine wave and nothing else. Yeah? This is just the field of the RFID reader, but you cannot make any, you cannot see if the device is currently computing something or not. You just see nothing. So that's why we put first a carrier subtractor here. This is just an analog circuit that subtracts 30.56 megahertz sine field from the side channel signal we want to acquire. And then it's fed into the oscilloscope. And then we, in the digital domain, after the digitizing, we do probably who in the room has built his own AM radio already? Quite a few. So this is exactly the same principle. You just need a diode and for rectifying and a capacitor as a low-pass filter. We filter at below 8 megahertz, which is quite a low value. So all information above 8 megahertz is discarded. And after this, you get, some months later, you get something like this. So you already see some information. If you think about it's a triple dash, you can really see 1, 2, 3. It might be, this might be the triple dash. But to verify it, you go through a profiling phase. So you can, of course, obtain DESFire cards of which you know the key, and we use them for profiling. So they've got the default key when they're delivered from the manufacturer, I don't know, FFF or A1, A0, A2, A3. And then you can make a power analysis on the plain text and on the ciphertext. So you can see where the plain text is processed, and you can see where the ciphertext is processed. And each of these little bumps here is when 1 byte of the plain text or when 1 byte of the ciphertext is processed. So you can be sure that in between these two time instants, there must be the triple dash encryption. Now, if you look at the time, how long it takes to load 1 byte of the plain text and how long the triple dash encryption takes, you can also make the assumption that there must be an 8-bit microcontroller inside the card plus an additional triple dash hardware, which is assisting the microcontroller. Now, knowing this, you can use another power model, for a Hamming distance model for the hardware chip and attack the hardware finally. And this also takes, again, some time. You also get some alignment issues. So this is again zoomed in. So you see these 3 bumps here, and this is zoomed into the bump. This is the first bump. And you pick one of these bumps to align the traces. If you do a differential power analysis attack, you always want all the power traces to be aligned very nicely in order to conduct the attack. And what we do now is we pick this reference pattern and align all traces with respect to this reference pattern. And we always send the same plaintext now. Send the same plaintext, and we see the second bump for the second attempt, sending the plaintext is somewhere else. For the third time, somewhere else. So we are sending the same plaintext, but the processing time of this device varies. So it makes the attack more complicated. It's kind of a side-channel attack countermeasure, maybe some dummy rounds or some timing countermeasure. But we also found a way of circumventing this you can read this in the appropriate papers, I'm not getting too technical here. And then the current state is that we can extract one of these keys. We still need 250,000 traces, which corresponds to 7 hours of measuring time. Of course, the bottleneck here is the communication with the card. You always have to communicate with the card. That's why it takes so long. And this basically means that you get full access to any MyFair Desfire card, Desfire MA3 ICD40 card. And this is our lab setup currently, so we just can insert any MyFair Desfire MA3 ICD40 card and let it run for 3 days and automatically extract all of its keys. And the equipment for this attack is pretty cheap, below 2,000 euros, and it's a non-invasive attack because it's measuring the electromagnetic field, so it has quite a high threat potential probably. Taking into account where this card is used, it's quite used for widely for some interesting applications. Right, this was, of course, this was responsive disclosure, and of course we spoke to the manufacturer a long time before we publicized this. So in the meantime, the Desfire card was discontinued about June 2010, and in the meantime NXP had a Desfire EV1, some follow-up product on the market, and is now selling these cards instead of the MA3 ICD40 Desfires. So this is a very good example for this circle I mentioned at the beginning. And yeah, you can analyze a lot of systems that use these Desfire cards. One example where the Desfire card is still used is the open card system in Prague. So the Czech Republic has invested 40 million euro for this project. About 500,000 cards are issued there. And it's a multi-application contactless card, so you can use it for the public library. You can also use it for parking in the city center if you need a parking space. And it's also most interestingly used for the public transport, so you can buy a yearly ticket onto your open card, which is already quite a lot of money. And usually these open cards are personalized, so you fill out a lot of forms with photograph and all your personal data is stored in this. But the data and privacy movement in the Czech Republic has put some pressure on the politicians, and now you can buy also anonymous open cards, but it's quite complicated because you have to fill in a lot of Czech forms, but it's possible, and I bought 10 of these, and we analyzed them and extracted the master key of one card and of other cards, and this master key is identical for all open cards. This is of course already quite good because you can format any card of these. And we extracted further all secret keys of all the applications. Yeah. So as I said, one is for the public library, one is for the parking, and one is for the, what was it? All right. And some of these vary, and some of them are the same. So we leave some of the efforts to you, and also what to do with the Clipper card. And so what we can do currently is access all files on the card, including personal information. And we intend in the year 2013 to maybe find out more things about this open card system. All right, it's time to get to the contactless payment system. But first I want to introduce another nice tool that we have developed, another open source tool. It's a Chameleon. It doesn't look like a contactless smart card, but to an RFID reader it appears like a contactless smart card. Its core is an Atmel ATX Mega microcontroller for €5. And what it can do currently it can emulate MyFair Classic cards, it can emulate MyFair Desfire cards, and it can also emulate MyFair Desfire EV1 cards. So all these cryptographic operations, Crypto1, Stream Cipher, and the Triple Des, and the AS128 is all implemented, and it's faster even than the original cards. And the advantage is here that this, compared to buying an empty card, is that this device can also emulate the unique identifier of the card. So if you buy a card, usually each card has a unique identifier, a unique serial number, and this device can emulate it. So as I said, it's an open source project. It would be great if people want to contribute, or if people would like to buy it. We also support this, so if there is more requests, we put more efforts in this side. And then next year there will also be the new mini version of the Chameleon. I can already announce this. So this is then credit card size. It's more easy to hide it in your purse. Before this you always had to wear a sweater and have half of the device in the sweater to pay with it. And now this will be small, so it's more easy to hide in the purse. Right. Yeah, one usage of this Camille device is this Siemens access control system. It uses my Classic 1K cards, and the secret keys in this system are the default keys. And they use the unique identifier, and there's something stored in the first block of the first sector. And then if the UID and the first block of the sector is correct, then the backend will authenticate and give access to some room. So we did this with Chameleon. This is the system in idle mode. And if you copy the content of one MyFair Classic card to a blank MyFair Classic card, and you hold it there, you see the light is red, you don't get access control. If you use the Chameleon, the light becomes green, you can just enter the rooms. Very nice. Now we finally come to the probably worst realization of a contactless payment system ever. So this is we called it ID card for employees. So we anonymized the manufacturer for years and years, but in this small trustworthy circle, we can now reveal that this is exactly what is in my student's identity card and many of your student identity cards in Germany in many different universities. What I can do is I can charge this, it's also called Mensa card. Yeah? You can buy it in the Mensa in the restaurant of the university, and you can charge it with up to 150 euro. And you can, it's also used for access control to some students' apartments, or for paying the washing machine, or for copy and print service, all this stuff. It depends on the university, and according to the manufacturer Intercard, there is more than 1 million cards of these in the field with exactly the same configuration. We interacted with the card, and we saw there is MyFair Classic chip inside. And we took again our RFID reader. As I said, this is an open source project, and on this RFID reader we have implemented a very efficient key recovery attack for MyFair Classic, old hat, but it extracts all 16 keys of the card in less than 10 minutes because this device has a very accurate timing, and the random numbers that are output by the MyFair Classic card are not random, but you always get exactly the same random nonce because of the timing accuracy of this device. If you use a commercial reader, it's far more complicated to really fix the random nonce of these cards. We tested it on the student identity cards. I tested it on my card and on the card of another student and on another student, and they all contain the same secret keys. This is, of course, a very good idea. This is an invitation for fraud. Yeah? Very good system design, yeah? To use MyFair Classic card and put all the same identical secret keys in all cards. Beautiful. So once you have extracted these secret keys, you can just, we went this repeated pay and compare approach. So we go paying and we look what has changed on the content of the card. You read out the card, what has changed, and we found inside of the card is an additional card number in addition to this unique identifier. And then there is the credit balance. It's just stored in plain without any additional protection. And there's some other data like last payment terminal used and so on. And so if you know this, if you know where the credit balance is stored, and if you know the secret keys, then you can now, of course, it's a contactless card, so you can manipulate someone else's card from a distance of 10 to 25 centimeters. You just have to get close to the pocket of the victim and manipulate the card. And one access to reading one sector or writing one sector takes 20 milliseconds. So 20 milliseconds is really quick. There's quite an attack potential here. Yeah, and we did some real world tests, of course. So we first took these cards. Of course, we did all these real world tests with the permission of the owner here of the University of Bochum. Yeah? So I went there. I explained that there are all the problems I'm explaining you now, and he was not completely convinced. But then he had got some special official member card, which was used by the employees of the university for open certain doors and other stuff. And he asked me if this card is also vulnerable. And I had programmed on this RFID reader, I had programmed some program that lights a green LED. It always tries to write 100 euros onto a card, and the green LED will only light up if this was successful. Yeah, so he gave me his card and asked if it's also vulnerable. And I just swept it over the antenna. I saw green LEDs on, okay. Gave it back to him and said, there's now 100 euro on your card. It is vulnerable. And he said, this has to be checked. This has to be checked. So we go to the main restaurant, to the Mensa, and we go down to the cash desk, to my favorite cash lady. And he said, can you find out how much money is in this card? And she said, yes, one moment, no problem. And he said, 100 euro. And then the guy was like looking left and right, running out of the Mensa. I said, Mr. Kasper, I have understood. We have got a security problem here. You can test whatever you like. So he said, eat as much as you can, test whatever you like. We don't inform the technical assistant. We need to find out what is really going on here. And that's how we, so my whole group, the whole chair of embedded security benefited, of course, from these tests. Yeah. So what we did is we cloned the cards. We just bought for 50 euros the empty MyFi Classic card of eBay and made some clones of cards that are existing in the system and paid with these cards. This was no problem. And then we just randomly modified the credit balances and paid with this counterfeit money. It was also no problem. What was quite interesting is that once you are in this position of the criminal, it's quite exciting. So I gave out these cards to my colleagues in the chair, and I told them, okay, you go, you hide the card in your purse because it's white, people will see that it's not original Mensa card, and then you pay, and please bring the receipt because we need to protocol how much money, what we have done, so that they can put the money back in the system. And the first day, I got 2 receipts out of 6 because they were also scared. The heart was beating. Because of being in this criminal position, they all forgot to bring the receipt. Of course. But then the next day, I came up to the cafeteria on top of the Mensa, and I saw already 5 people there with a big ice cream. And I thought, I also want to have an ice cream. And I went to the lady, and I said, I put my purse with the cards on the reader, and I smiled at her. I said, she smiled at me, and I would like 1 ice cream. And then she said, and now you want the receipt, yeah? So because there were 5 people. Yeah, there were 5 people buying ice cream, and they all wanted a receipt for the ice cream. Yeah, we had a good time. After 1 week, we were already very, very, very fat. We also tried to produce completely new cards. So you guess a new card number and you put some random money on it, no problem. So nothing in the back end, no effective measures at all. Beautiful. So what the criminal could is hard work. Do you see the sweat? Sweating. Right, what the criminal could do now is, of course, he could sell these cards. Yeah? He could dump some card and then sell it to other poor students, have a top-up service, like pay €1, get €3, something like this. But of course, I mean, who is going to do this? No one is going to harm your own institution. You don't want to harm your own university. No one is going to do this, and no one is going to do such fraud. You will still get into jail. Still, if someone would do this, criminal would become rich, but this issuing institution would be bad because people would be paying with money that has never been paid into the system. This would, of course, be a problem, but no one is doing this. You could also emulate cards, if, for example, if you have the Chameleon, or if you have an NFC-enabled mobile. You can just, on every payment, emulate a new Mensa card, and this is of course difficult to track in the backend then, because on every payment you have a new card number and a new credit value. It will be difficult to detect the fraud in the backend. Right, then I thought, okay, no one is going to do the fraud, but what about the denial of service attack? So we assume that there's an attacker and he's running around with the reader and he's setting all cards in the field manually to €0, hard work. He could take the reader then, our reader, and put it in the standalone mode and hide it somewhere close to the cash desk, for example, where the people are queuing, and set all cards to €0. It's a good idea. This is what the evil attacker would do, but if you think about it, people would just go complain, I have €0 on my card, and they would fix it somehow. And what would happen if it's a nice attacker and he charges the card? Let's not say €100, let's say he charges with €23.48. Yeah? Then people would not even notice this. And there might be a lot of people who are not willing to contribute to the attack, but they will contribute because either they will not notice that they have more money on their card, or they just will notice, or who will complain if there is more money on the card. So this is the really scary attack, I think. This is what, on the long term, where they would have to shut down the system, because people are paying, they're participating in the fraud without unwillingly. Yeah, my favorite attack, the cashback attack. So what you can do is you can get an anonymous Mensa card, And you go to the cash desk, you give them €10 deposit. And then I did this, I went to the lady at the cash desk, bought this card and went around the corner and charged it with €50. And then 1 hour later, I went to another cash desk and I said, okay, I don't need this card anymore. Can you please pay out the money on the card? And yes, it works. So this is the wet dreams of the cryptographers, converting zeros and ones to real cash. Really beautiful. Best part. Now, what does it mean for mafia then? So if you look on the left top, we've got a new M here, where you can walk in, and this is the Mensa Freddy, and he is selling MyFair Mensa cards. And you have got some new options here. So it's, hey, old Kommilitone, shall I read cards? And you can say, one is, I am hungry, please load some money on my Mensa card. And the 2 is, do you still have a chameleon kit for me? I have to emulate something. And number 3 is, I need some cash. Can you pay out my remaining credit, please? Yeah, and this is the Mensa Freddy. So, if you're a system designer, what can you do? Of course, you all want to, you know this, you all want to use peer-reviewed cryptography, which is ciphers which are known to be good. Of course, you can add some obscurity on top of this. It doesn't harm the thing. Yeah? If you want to use some proprietary thing, of course, if the core of your application, if it's some good peer-reviewed crypto, okay, go on then, put some obscurity around it. It cannot harm the application end of the day. What you should keep in mind is that what you have seen, physical attacks, for example, side-channel attacks, reverse engineering, they're always a potential issue. And that's why you have to use certified devices, or you have to follow the ongoing security research. So what's the point if you have a microcontroller and you add an AES 256, you implement it on this microcontroller, and the attacker comes and just reads out the program code because there is some fault injection attack to read out the microcontroller, and he gets all your secret keys. What's the point in implementing an AES 256? What if someone measures 100 power traces of this microcontroller? You have got AES 256 in the microcontroller, and the attacker still gets the key. What's the point? So you have to take these physical attacks into account when designing the system. But these embedded systems, they're only the first line of defense, right? So not unlike in this contactless payment system, you can do something to detect fraud and have a fallback plan in your backend. Like if a key is compromised, you should have a mechanism to have another new cryptographic key, or use public key cryptography. There's a lot of options. Have shadow accounts for Mensa card thing. And yeah, if you are a system designer, do not educate your attacker. I'm doing this for 5 or 6 years now, and what I always experienced, where I always benefited from, is that the companies put some products on the market which are in the first place weak and then need to be upgraded, that are easy. So you can learn a lot already from this first series of devices that you can attack, and then they improve something in the second generation of this product, and usually you would not be able to break it. But with the knowledge you already got from the first generation of this product, it's an easy step to also break this more secure devices. So that's what we saw with the Xilinx FPGAs, for example. Yeah, that's the end of my talk. Thank you. So if you want to come to Bochum and study IT security, you get food for free. It's a very nice place.
Yeah, thank you, Timo. So I guess there might be some questions. So if you'd like to ask a question, please queue on the microphone. Do you have any question from the internet?
There's one question from the internet. You did say you extracted not only keys but also information from the card. Are the protocols to talk to the card standard?
Yeah, the protocols to talking to the MyFair Classic cards or MyFair Desktop cards, they're standardized, so you can. And they are known on the internet. You can look on the Proxmark sites, and in these days you can find these protocols somewhere using Chinese Google or so, google.ca. It's all on the internet in these days, and there are already some devices like our reader which are implementing the protocols for these MyFair Desktop cards and MyFair Classic cards.
Number 2, please.
Yeah, I got 2 little questions. First, the student card was replaced, the MyFair through a Desfire card. And I would like to know if you cracked both cards or just the MyFair Classic card?
So it's in this system these days they've upgraded to MyFair Desfire, but of course all the old MyFair Classic cards, they are still valid and it's still all working. So it's just when I come there, I always get a special message that the system integrator put there that says please greet the customer. And so always if I buy something, they are greeting me, and he cannot delete it from the system. He cannot find me anymore, which is a good sign. It looks like there is no link from my name and my Matrikelnummer to my Mensa card, which is quite good.
Yeah,
And now these upgraded Desfire cards we have not further analyzed because, oh my God, it's our university.
So, and the second card is the second question is you said the chameleon. You got a few. Can we buy a few devices here on the C3 or?
No, I did not bring. I will do it. I will bring some. I promise. I will bring some kits to the next to the 30 C3. But currently I have not brought it. It's just the layout. It's a simple layout. You can produce it on your own. It's on a home cooking.
Okay. Thank you.
Well.
The guy number 1, please.
You mentioned that it is a bad design to use the same secret for all cards. I wonder what is the workaround. Would you have to store like the secrets you use for and remember for every serial number of the cards the used secrets and store it in the back end systems, or how would it work to use a different secret for every card?
Yeah, one option is, as they did in the keylog case, where you've got this master key, but it's also bad because you also have a single point of failure. And once the attacker knows the master key, he knows the other keys. And better option would be something like use public key cryptography. Then there is a public key in the card, if you have enough computational capabilities, which is these days possible. There are IFIDs who can do ECC, and then use public key cryptography.
But in this case, they use the cheap MyFair cards. So could they work around it? Like they would have to build their own secret on application layer to work around this.
So what they could do is they could do some way of key derivation, and this would of course make the attacks of this system by orders of magnitude more complicated. The current state is you go to someone else's pocket and it has the same secret keys and you just manipulate his card and he didn't even notice. If his card would have another secret key, this scenario would not be working anymore. First would have to have access to his cards for 10 minutes to extract the secret keys, and afterwards manipulate the content. That's why it would make the attacks a lot more complicated.
What I do not understand is how does the legal card reader knows the secret of the correct secret of the card?
Yeah, so there are either secure access modules who can compute keys, derive keys, or you implement something similar to the keylog system, where you take the card number, unique identifier of the card, or both. If you would check the unique identifier, would also be good, and derive the key of the card from this information using some master key, using some AS or so, or using some hash function, whatever.
Number 2.
Yeah, you talked about that all the cards have the same keys. I am assuming you talk about
of one instantiation. This is
okay.
For the Ruhr University. It is one.
Yeah,
I once did a lecture in Hochschule Bonn-Rhein-Sieg, and they had different keys.
Yeah, genau. I checked that too. But the both key A and B for the first sector are always the same on different universities.
Are they? But probably because these sectors are used, because the credit value is stored in
yeah, they are stored in now. But the first sector, they put there some proprietary MyFair application directories. Somewhat, they all look the same at different universities, but always have the same keys.
Are you having this business already then?
No, I haven't a university that allowed me to check buying things, but I was at a nearly same stage, but nobody allowed me to try it.
Oh, poor. That's bad. For me, it was very good because I got this paper on financial crypto in Tenerife, the beach, because they allowed me to do it legally. Otherwise, I wouldn't have been able to do it. No.
Okay, thank you.
You're welcome.
Okay, the guy with the number 54201.
Yeah, that's me. You said that the card was used in universities. What were the other uses, like company canteens or?
I'm not. I don't really know where it's in all the universities, and it's in some companies like big companies where you've also got kind of Mensa and pay there with contactless.
But the main use was universities.
Main use is universities, I think. If you look on the card reader and it says Intercard, you have a high chance that it's the similar system.
Thank you.
Okay, please.
Just one thing. Lots of banks use them to authenticate their personnel and also for payment.
Oh.
In their buildings, because they have like, they don't want the employees to leave the building, so they have like wash machines there, you know, lots of things, food stuff, and they pay with it.
All right, thank you.
Thank you.
What are the defense strategies from the company side to, I mean, we saw jitter on the power traces, obviously the modern card add jitter. Are there other strategies they add to?
Now this question relates to NXP, to the card manufacturer who is producing now the follow-up product, the DESFA EV1, which is like EAL, I don't know, 4 plus or 5 plus certified. And what they currently do is, if you look at a power trace, you saw before that you could see some like 3 bumps or so. At least you could see something that the card is doing something. If you look now at a DESFA EV1 card, it starts consuming a lot of power. So they are using a noise countermeasure in addition. And just the power consumption becomes very, very big, and it becomes quite random and stable. And on the first glance, you cannot. You can spot some things, but you cannot see where the encryption is, and you cannot attack the encryption. So I have no clue. You have to ask someone from NXP what exactly they put inside. But I guess that they use some masking and hiding and additional some noise. And this will probably be secure for most of the applications and for the next few years.
It's kind of a signal-noise ratio.
The usual measures are that you do some hiding in the time dimension, that you add noise, and then on the algorithmic level that you put some masking. So you mask all the values with random values. So if you make a power analysis, like you cannot see the real values anymore.
Okay, number 2, please.
Well, first of all, thanks for the talk. It was awesome.
Thank you.
And
you get a free Fiege beer after the. You can collect it.
Secondly, rather non-technical question. It strikes me that if you go to Philips buy such a MyFair thing, then you don't get a working crypto system, but building blocks to build your own system. So kind of like a Lego set, right? So it is up to the integrators, the integration guys, to build their own crypto system. And that ends up with problems like they put in the money value. It's just readable clear text value and not protecting that additionally.
Absolutely.
That seems to me like a structural problem. Since you've got quite a background on this
I think the problem is in all the companies, that's what we also heard today in the morning about the electric locks, is that there is a lot of companies who they are like a family company who have like 500 workers, and they just cannot, they just don't have a cryptographer in the company, and they say, okay, we want to do something secure, and they buy some product, and then they say, oh, default key, let's use the default key in all our access control, because they think, aha, now it is encrypted.
Exactly.
So that's why we have the new company Chaos, Kasper and Oswald, so all the people who need this cryptography experience, they can come to us and
so you have a solution for that kind of structural problem.
Yeah, this is on the right bottom side. Yeah, it's a very new company, only founded 2 months ago.
All right, thanks.
Thanks for the advertising. You get 2 Fiege beer.
Okay, number 1.
Yeah, I've got another question. If you've got RFID card, how do you find out which chip is inside it?
So it depends. First of all, RFID is a very wide world. Yes, you have
access control
125. Card. Yeah, you can have a 125 kilohertz access control card, or you can have one working on 30.56 megahertz, whatever. So assume we are in the 30.56 megahertz HF range, then they will all obey, most, like 95%, will obey the ISO 14443 protocol. And then at the beginning of this protocol, you get some you get some answer to request. In the protocol step, there is somewhere an ATR, and the card gives you some information. And from this information, there's for NXP cards, for example, there's an application note identification of MyFair cards, and then according to this ATR you can see what type of card it is. So first step is identify the frequency. It's most likely 120 kilohertz or 30.56 megahertz, and then look at the information that the card gives back to you according to the ISO standard. And then there is usually some, by the manufacturer, some documents that, or you just buy some commercial reader. There comes a program with a commercial reader. You put the program, or buy this NFC smartphone and get this NFC tool and put the smart card on top of it. It will tell you what smart card it is. If it's not reacting, it's probably a 125 kilohertz smart card. And you have to do the same for the 125 kilohertz domain.
Okay.
Complicated, no?
Number 4, please.
Did I get this right? It will take 10 minutes to read out the keys of a completely new card.
MyFair Classic card is one sector key is 30 seconds. With our implementation, 30 seconds for one key. So you put the card there, you wait for 30 seconds, and you have one MyFair Classic key. But this applies to the MyFair Classic. Do not confuse it with the MyFair Desfire card. For the MyFair Desfire card, 7 hours for one key.
Okay, 7 hours.
Yeah, and this is 7 hours and 250,000 traces. If you compare this with 10 traces for the keylog remote control, you just needed 10 power traces, and now you need 250,000. It is because of the countermeasures and the disturbing strong RFID readers field.
Okay, do you really need those 7 hours, or could it be that if you're lucky, you find a matching key after 10 minutes or 15 or 20?
No, that's very unlikely. So usually you will need some hours for it. It's an average value, 7 hours. But these attacks can still be improved, like you can do template attacks and all these things. Okay. But it's in general sufficient if you have one card, you can borrow it for a while and extract the key.
I need only one card, and then, okay, I see.
So you can put any card into this lab setup, you press on play, and then you go away, and you work, and after 3 days you come back, and you have all the keys, all the applications, all the keys, and all the content of this Desfire card.
Thank you.
You're welcome.
Number 2, please.
Have you tried this with other Mensa cards from other universities?
No, only yes, but not officially. I think. I think I only read out the cards, but I guess I never went eating for free.
Okay, I got an Intercard here. Is it just the same?
Yeah, I think this what's the name of this manufacturer who sells the readers or so. Or maybe who sells this the system. Yeah. Maybe it's good. Maybe you are on the lucky side. But be careful, yeah. That's the one step to jail.
Just in addition for him, in Magdeburg it's also possible. We have the MyFair Classic and the new Desfire, and the Classic is of course flawed. You can get free food.
No one is hungry. Good.
Good news from Magdeburg. Number 1.
Yeah. Do you know whether it would be possible for the card manufacturers to just put in a little white noise generator into the IC and just put white noise on the antenna whenever it's doing cryptography, so that it just blocks out all your side channel signals?
Yeah, this relates to the question we had before here. What countermeasures can the manufacturers put into the car? So the thing you mentioned, just produce a lot of noise, is one of these countermeasures. But in the end of the day, if you add noise for the attacker, it just means you need more measurements. Yeah. If you then acquire 2 or 3 million measurements, you will still be able to get the card. So you need to find a compromise between the different countermeasures, which is appropriate for a system. And you will come to some point where you say, no, it now takes 1 year and 10 million traces. Now my card is secure enough.
I mean, if the white noise would be like 40 decibels above the side channel, you would have a real hard time seeing any signal in there, even if you have so many samples.
No, I would say the white noise just averages out on the long term. So if you average over this white noise again and again and again, it will become 0, and only the side channel leaker will remain. We can talk about this offline. I can explain you how these attacks work then.
Okay, thank you all. Thank you, Timo, for the great talk.
Great audience.